This is the first of a series of lectures on the Zermelo Fraenkel axioms of set theory. So this will be the first introductory talk on the axioms, where I'll just give a sort of informal overview of them, and in later lectures I'll be going through the axioms in a bit more detail. And so first of all, I'll just state the axioms, again a little bit informally. We have extensionality. So what extensionality says is that a set is determined by its elements. Next we have foundation or regularity. This says that there is no collection of sets, each of which is contained in the one before. So you can't have A1 contained in A0, A2 contained in A1, A3 contained in A2, and so on. So what we're saying is that an infinite sequence like this is not allowed. In particular, this means a set can't be a member of itself, because that would give you an infinite sequence. Next we have pairing, which is a rather simple axiom. It just says if you've got any two sets, then you can form a new set whose elements are the two sets A and B. And we have union, which says that if you've got sets A, B, C, and so on, then you can form their union, which is the set of elements contained in one of these. Then we have the axiom of infinity, which says there is an infinite set. So for example, you might take the set 0, 1, 2, 3, and so on, whatever that means. Then we have power set, which says that if you've got a set, then PA is a set which is equal to the set of all subsets of A. And we have the axiom of separation, or axiom of subsets, which says roughly that any subset of a set is a set. Okay, that seems to be a little bit circular, because what do we mean by subset? Well, when I discuss the axiom in more detail, we need to give a more precise version of it. Then we have replacement, which says the image of a function on a set is a set. And again, we have the question, what do you mean by a function? And I need to describe that in more detail later. And finally, we have choice, which says, suppose you've got several sets. Suppose I've got a set of some orange points and a set of some blue points and another set of green points and so on, and several other sets. What choice says is I can pick a single element of each of these sets, and that forms a new set. So that looks kind of obvious, but it is in fact the most controversial of all the axioms. So that's a very informal version of the axioms. So to state them a little bit more formally, first of all, they need to be stated precisely in the language of set theory. And the language of set theory contains two important symbols. It contains membership and equality. So membership means A is a member of B, and equality means A and B are the same, whatever that means. And we need to form sentences using first order logic, and just give a very quick reminder that first order logic means you can form sentences using and or not for all and there exists, or for all x and there exists an x. So for example, if I want to say A is a subset of B, usually denoted by that, that means for all x, for all sets x, x is in A implies x is in B, where implies can of course be formed out of the symbols and, or, and not. So one thing we ought to do is convert all the axioms into this precise first order logic version. Originally set theory was based on the axiom of comprehension, which says for any property P, we can find a set of things with property P. And the trouble is, as everybody knows, this leads immediately to Russell's paradox. So if you take P to be the property that A is not a member of itself, and you form the set of all sets that aren't a member of themselves, then you quickly get a contradiction. So the axiom of comprehension just doesn't work. If you look at the axioms of Zermelo Fraenkel set theory, a lot of them, pairing, union, infinity, power set, separation and replacement, are in some sense special cases of the axiom of comprehension. So you hope that by keeping these forms of the axiom of comprehension and discarding things like this, then maybe you won't get into a contradiction. One of the properties of this is that the concept of one of the problems is that the concept of a property is actually rather tricky. I mean, what do we mean by property of sets? So you might say, well, it has to be a property defined in some language, and you might take, say, for instance, the language of first order set theory. The other problem is, what do you mean by a set? And it's actually very difficult to pin down a precise definition of a set. So you can think of informally a set as being a collection of what? Well, it might be a collection of sets. Well, you see, that's not really much use as a definition because it's kind of recursive. In order to know what a set is, you first need to know what a set is. So this doesn't really work. So how can we try and make sense of this? One way, instead of trying to just take all sets, what we can do is we can build up the concept of a set by starting with easier sets and kind of working upwards. This leads to something called the von Neumann hierarchy, where you start with a collection of sets like this. First of all, you start with V0. This is just going to be the empty set. There's absolutely nothing in it, and it's not very difficult to think of the concept of an empty set. And V1 is going to be all subsets of V0. So V1 has only one element, which is the empty set. So we can think of V1 as being the set containing just the empty set. So this is the empty set, which is the set containing absolutely nothing. And V2 is going to be all subsets of V1. So V1 has one element, so V2 has two elements, which are the empty set and the set just containing the empty set. And V3 is going to be all subsets of V2, so V2 has two elements, so V3 will have 2 to the power of 2, which is 4 elements, and V4 will have 2 to the 4 equals 16 elements, which for obvious reasons I'm not going to write them out because they get to be a bit of a mess. And we can go on like this for all finite numbers, and it's sort of fairly clear what we mean by this. And then we're going to do V omega to be the union of V0, union V1, union V2, and so on. So it's all things you can form by iterating this power set operation a finite number of steps. And now we can continue. So V omega plus 1 is going to be all subsets of V omega. And actually there are some philosophical problems about what we mean by all subsets, but let's ignore those for the moment. And now we can continue. V omega plus 2 is all subsets of V omega plus 1. And we go on like this and we get to V omega times 2, which is V omega plus omega, which is the union of V omega plus 1, V omega plus 2, and so on for all finite integers. And then we can continue and get V omega dot 2 plus 1 is the set of all subsets of this. And more generally, for any ordinal, we can form a set V alpha by sort of repeating this process. We sort of alternate with doing power set operations a countable number of times, then collecting together everything we've done before. You can actually make sense of this in the language of first order logic, and you find that you can actually prove as a theorem that all sets are given by V, which is the union over all alpha of V alpha, although making sense of this takes a little bit of work. So this is called the von Neumann hierarchy, or the von Neumann way of picturing the universe. In order to see where the various axioms occur in this, well, the power set axiom is used in going from V alpha to V alpha plus 1. You see, you're taking a power set each time. The axiom of infinity is needed in order to get to V omega, because to form the union of an infinite collection of sets, you need to be able to sort of define what infinity means, and that needs the axiom of infinity. The axiom of foundation and the axiom of union are used in collecting together the sets at each stage. So V omega dot 2 is the union of V omega plus 1 and so on, and doing that actually requires union in infinity. The axiom of foundation is sort of used to show you get all sets like this, to show that V is actually equal to the union of all sets like this. So that gives a sort of rough informal model of what the collection of all sets is supposed to look like. And how can you picture a set? Well, the usual way of picturing a set is to think of a set as being a collection of its elements like that. So we might have the set of all primes, which you can picture as 2, 3, 5, 7, and so on. Well, what we would really like is for A, B, C, and so on to be sets as well. So we start getting this should be a set consisting of A. Well, A will be a collection of things, and each of these things will be a collection of something or other. So you can write down a set by writing down a vast number of these curly brackets, and this gets a little bit tricky to write down. So what you can do instead is write down a set as a sort of tree with branches given by A, B, and C, and so on. And now A, B, and C are also sets, so you should think of these as being trees as well. So a set is now going to start looking something like this. It might be a collection of trees looking like that. So and this would be a picture of a finite set. And what you should do for infinite sets is imagine that at each stage you're allowed to branch out an infinite number of times. So you might, for instance, picture a set that looks like this. Then it has another branch with 3, and then a branch with length 4, and so on. So you can sort of have infinite numbers of branches of gradually increasing length. You might think you would be allowed to have branches of infinite length as well, but the axiom of foundation actually rules that out. The axiom of foundation says you can't have an infinite chain of sets each containing the next, and that actually says all branches of this tree have to have finite length. So that gives a sort of informal way of picturing a set. You can think of it as being a tree with all branches of finite length, but a possibly infinite number of branches. And also this condition that the axiom of extensionality means that, for example, this tree and this tree have to be different because you're only allowed one copy of each object in a set. Now we come to a rather knotty question. Are the axioms consistent, and do we actually have a model of them? In other words, how do you interpret an axiom? I mean, you can think of a set as being informally some sort of tree, but when you start making these trees infinite, it becomes really rather unclear what you're actually talking about. So I'll finish this lecture by discussing the possible ways of interpreting the axioms. First of all, there's a sort of Platonic way of picturing sets, where what we're doing is we look at the collection of all sets, and we imagine that somehow this set of all sets exists in some mystical way, and the axioms are an attempt to describe its properties. Well, this has one serious problem. First of all, we don't know what a set really is. A rather more serious problem is, why is the collection of all sets not a set? Well, it can't be a set, because if we try and make the collection of all sets into a set, then we run into Russell's paradox. And it's very hard to think of any really good justification why, if we have a collection of all sets, why this collection shouldn't also be a set. For example, the axioms allow us to quantify over all sets. That means we're allowed to say for all sets some other property holds. And if we know all sets well enough to quantify over them, it's, why can't we also collect them together into a set? So the Platonic interpretation of set theory isn't really completely satisfactory. A second way is to look at the von Neumann hierarchy. So we have V0, V1, V omega, and so on, V omega dot 2. And we might imagine that if we go on long enough, then we can actually get to a V alpha that's a model of set theory. And it turns out to do this, you can do this provided alpha is something called an inaccessible cardinal. And an inaccessible cardinal means it's not a successor of another cardinal, so it's not a cardinal plus one, and it also means it has to be regular, which means it's not the union of less than alpha smaller cardinals. So every time we find an inaccessible cardinal, we can find a model of Zermelo Fraenkel set theory, provided we assume the power operation is well defined, which is another rather tricky problem I'll discuss in a later lecture. So the von Neumann hierarchy does actually give you models of set theory, except for two little problems. What is the power set of an infinite set, and do inaccessibles exist? And it turns out it's actually very difficult to explain why inaccessible cardinals should exist. So the von Neumann hierarchy gives you a good model of what a model of set theory looks like if such models exist, but it doesn't really give a very convincing explanation of why such models should exist. A third view is the multi-set, so the multi-universe view. So this means that that there isn't one grand model of all sets. Instead, we get lots of different models of Zermelo Fraenkel set theory, and there's no particularly good reason for preferring one of these over another. So this is like the multi-universe view you sometimes get in various models of quantum mechanics, or for that matter in various comic books, where if you watched any Marvel movies, you notice that there are several different copies of the current universe in which different things happen. And the multiverse or multi-universe view of set theory says that there's something similar going on in set theory. There are lots of different models of set theory, and there's no special model that's better than all the others. And this has a problem. Why do any models of set theory exist? Turns out once you've found one model, that we have lots of ways of constructing other models, but it's very difficult to explain why there should be any model at all. I mean, you can sort of justify the existence of models by taking the Platonic or von Neumann hierarchy view, but as we said, there are problems with both of these. So a fourth approach is formalism. So formalism says you ignore meaning of the axioms and you just investigate their consequences. And whenever you proved a theorem, you found a new fact that there's a theorem that's a formal consequence of your axioms. And if you ever run into a contradiction, you found this interesting theorem that these axioms of set theory are contradictory. So you don't really, formalism in theory, you don't really worry too much about whether axioms are true or meaningful. You just sort of investigate their consequences. And the problem here is, why are you investigating these axioms? I mean, formalism doesn't really explain why these axioms are interesting. Why don't we just select some completely random collection of statements in the language of first order logic or set theory and investigate their consequences? So, formalism is a sort of, it's like sitting on the fence. You don't have to make your mind up about whether these axioms are consistent or not. So you don't have the disadvantage of having to worry about consistency. On the other hand, it makes mathematics seem like a rather dry and pointless occupation. The fifth one is pragmatism, which is a bit like formalism. You sort of ignore whether the axioms are true or not, and you just assume they're true and get on with proving theorems like Fermat's last theorem or the Riemann hypothesis, and just don't waste time worrying about whether the axioms are true or not. The sixth approach is finitism. Finitism says, some of the stronger forms of finitism say the axioms are meaningless nonsense. That infinite sets don't exist, and uncountable infinite sets exist even less than countable infinite sets exist, and who cares what the consequences of the axioms are because they're not actually describing anything anyway. This is a perfectly valid point of view, and there are some mathematicians who will go for this view. There's a problem with this view too, though. The first problem is, why do the axioms work so well? I mean, a century of working with the axioms show that they really do seem to do useful things, like explain why Fermat's last theorem is true, and if you simply reject them, then you've lost most of mathematics, which some people don't regard as a bad thing, but whatever. So that's a quick overview of the axioms. The next few lectures will each be about one or two of the axioms, where I'll be discussing in more detail what they're actually used for and what happens if you don't assume them and so on. So the next lecture will be on the axiom of extensionality.